conditions.
That's remarkable.
It is. It suggests that by subtly manipulating the phase geometry at the boundary of an experiment, we could actively alter fundamental wave interference patterns. It opens entirely new avenues for potentially controlling wave phenomena using geometrically patterned boundaries, derived directly from rigorous wave theory.
Moving to a different kind of interaction. We see synchronization everywhere in nature, don't we? Fireflies blinking in unison over vast areas, neurons firing together in the brain, even planets falling into orbital resonances. It seems like a fundamental organizing principle. Can this phase field framework offer a rigorous mathematical explanation for how things lock in or synchronize across such diverse systems?
Yes, absolutely. The concepts of phase and phase locking are central to synchronization, and this framework provides a rigorous mathematical foundation for understanding this collective phenomenon often called entrainment.
Entrainment. Okay.
We can model this using a system of coupled oscillators. Imagine you have nondular individual oscillators, maybe like those fireflies or neurons. Each one has its own phase and an intrinsic natural frequency, omega, at which it would oscillate if left alone.
Each one has its own rhythm.
Exactly. But these oscillators are not isolated. They are connected to each other. They can influence each other's timing. And crucially, in many systems, they are also connected to a central pacemaker or phase anchor, which itself has a specific phase. Let's call it $5. Think of maybe a dominant rhythm or an external driving signal.
Like a conductor for an orchestra.
A very good analogy. Now, the dynamics of these oscillators, how their phases fight or change over time, are precisely described by a well-established system of equations, often based on the Kuramoto model, famous in mathematical biology and physics.
The Kuramoto model, okay.
This model describes a rate of change of each phase as being influenced by its own natural frequency. The average influence from all other oscillators, typically involving terms like Frunghai, where Causality is the coupling strength, and the influence of the central pacemaker, with the term like K-phi, where K is the pacemaker coupling strength.
The sign terms capture the phase difference influence.
Exactly. The sign function naturally captures how the tendency to synchronize depends on the phase difference maximum pull when they're 90 degrees out of phase, zero pull when they're perfectly in sync or perfectly out of sync.
So, can we prove they will synchronize?
Yes. The significant point here, mathematically, is that the pacemaker entrainment thresholds are rigorous. This means there are precise, mathematically provable conditions that can be derived from analyzing the stability of these coupled differential equations. These conditions typically relate the strengths of the couplings to the spread in the natural frequencies and the difference between the average natural frequency and the pacemaker frequency.
So, math tells you when they will lockstep.
Precisely. Under these specific, definable mathematical conditions, the analysis proves that the entire group of oscillator, or a significant fraction of them, will predictably and reliably synchronize, or lock in, to the central rhythm of the pacemaker oscillants. Their phases will converge towards the 6an. These thresholds aren't just empirical observations, they are fully derivable from the stability analysis of the governing equations.
That's powerful.
It is. It directly ties abstract phase field concepts, like a central phase anchor to a widespread natural phenomenon, synchronization. It unequivocally shows how the mathematical principles of phase dynamics govern collective behavior, providing a quantitative, provable explanation for how these phase anchors can drive a group of disparate elements to act in unison. The math provides the conditions for coherence to emerge.
This deep dive has meticulously explored the mathematics of the time-phase field. And you've really emphasized how much of it rests on solid, provable foundations within existing physics and math. So let's now really clearly draw the line. Let's distinguish what aspects of this powerful framework are already firmly established, rigorously proven, and what remains as exciting but currently unproven testable predictions that still need the lab to validate their physical reality. This distinction feels absolutely crucial for understanding where this framework stands right now and where it's headed.
Yes, that's an essential distinction to make, absolutely. And it's key to appreciating both the rigorous foundation we've built upon and the cutting edge where this inquiry is pushing. Highlighting the provable parts allows us to build immense confidence in the internal consistency and the mathematical power of the framework itself. These aren't guesses or hand-wavy arguments. They are derivable truths within the system, built upon well-established mathematical and physical principles.
Okay, so let's list them out. What's definitely in the proven column based on our discussion?
All right, let's recap what is firmly established and proven within mathematics and standard physics from everything we've covered. First, the phase field variational structure itself. Defining a system using a Lagrangian density, deriving the Euler-Lagrange equation for the field's dynamics, and calculating its stress-energy tensor, these are all standard applications of variational calculus and classical quantum field theory, entirely consistent with established physics. The mathematical machinery is sound.
Okay, the basic setup is standard.
Correct. Second, the fact that equal energy phase-different superpositions produce different nodal geometry. We showed this with the simple membrane example. It's an unequivocal mathematical demonstration using basic wave superposition, changing the phase difference. Varphy rigorously alters the resulting spatial pattern, the nodal lines, even when the total RMS energy is fixed. That's just math.
Provable wave behavior. Got it.
Third, the principle of hexagon versus decagon pattern selection via amplitude equations. This is a well-established result from the sophisticated theory of pattern formation. The technique used, multiple scale analysis, is a standard mathematical tool, and the stability criteria for different patterns based on minimizing Lyapunov functionals derived from these amplitude equations are mathematically rigorous. That's proven pattern theory.
Standard pattern formation math. Check.
Fourth, the generation of spherical Fibonacci patterns using irrational angles and the properties of the Hopf vibration regarding equidistribution. These results follow directly from Weyl's criterion for uniform distribution, and the theory of Kronecker flows on circles and tori. These are standard, provable properties within number theory, dynamical systems, and geometry, establishing how specific types of numbers, irrationals, lead to uniform spatial coverage and complex structures.
Number theory giving geometry. Proven.
Fifth, spectral asymptotics unequivocally guarantee symmetry-dependent finite parts in vacuum energy, like the Casimir effect, at fixed area and perimeter. This is a provable result emerging from quantum field theory calculations in confined geometries and the mathematical field of spectral geometry. The math linking geometry to vacuum energy differences is solid.
QFT and geometry connection is proven.
Sixth, the fact that boundary phase geometry shifts interference envelopes at fixed flux. As we discussed with the double-slit example, this is a provable mathematical consequence derived by solving the Helmholtz wave equation using standard Green's function methods with specifically constructed spatially modulated Robin boundary conditions. Wave theory predicts this outcome.
Wave equation solution. Provable.
Seventh, pacemaker entrainment thresholds are rigorously derived mathematical conditions. They come from the stability analysis of systems of coupled differential equations, like the Kuramoto model. The math clearly defines the conditions under which synchronization is guaranteed to occur.
Stability analysis of oscillators. Proven.
And finally, eighth, the concept of symmetry-dependent minimizers in variational PDEs is standard. This is fundamental to the calculus of variations and the study of partial differential equations. It's mathematically proven that minimizing certain energy functionals, which include symmetry-breaking potential terms, like our dollar for the leaf, will lead to distinct solutions with different shapes or symmetries, such as sharp versus round forms.
Variational calculus results. Standard and proven. That's a truly powerful list of what's already mathematically secured and stands on incredibly firm ground. It really builds confidence in the framework's internal logic. But as you said, this isn't just about elegant theory on paper. It's about potentially describing and maybe even interacting with physical reality itself. So what are the concrete testable predictions? What are the empirical challenges, the specific hypotheses waiting for experimental verification that would validate the physical reality of this mathematical elegance in the laboratory? Where does the math meet the experimental method?
This is exactly where the framework makes its leap from rigorous mathematics to exciting empirical science. These are the falsifiable physical predictions that need the lab to confirm or refute their physical manifestation. These are the experiments waiting to be done. One key prediction stemming from the spectral asymptotics is the potential measurement of Casimir corrections between matched cavities possessing different symmetries. For example, building a hexagonal cavity and a decagonal cavity, carefully engineered to have the exact same area and perimeter, and then attempting to measure the predicted tiny difference in the Casimir force between them. That would be huge.
Measuring the energy difference due to shape alone.
Another really compelling prediction involves tissue morphogenesis switching. Drawing from our discussions on pattern formation and variational coupling, the framework predicts that it might be possible to observe distinct changes in biological forms, maybe switching between different branching patterns or shapes in a controlled biological system by solely altering the phase fractions governing an underlying control field while keeping the overall available energy fixed. That would be direct phase control over biological patterning.
Change the phase input, get a different biological shape. Wow.
Similarly, we predict that we could potentially demonstrate colloid or metasurface ordering switching. Imagine having tiny particles or engineered optical elements arrange themselves. The prediction is that we could cause these macroscopic patterns to transition between, say, hexagonal and decagonal arrangements simply by varying an applied phase program, maybe using light fields, at fixed input power. That would showcase direct control of macroscopic pattern selection through phase manipulation.
Switching material patterns with phase, got it.
The framework also hints at potentially measurable effects in condensed matter, like predicting a specific scaling for the coherence lifetime of water molecules with the mathematical properties, like irrationality class, of an imposed electromagnetic driving field fraction. It suggests that maybe golden mean-related frequencies might yield maximal coherence lifetimes. That's very speculative, but potentially testable.
Phase affecting water structure lifetimes. Interesting.
And finally, directly testing our discussion on the double-slit experiment. A critical prediction is that double-slit interference distribution changes could be observed under symmetry-coded boundary phases. This means setting up a double-slit experiment, applying specific patterned phase modulations, using sophisticated techniques, to the material right at the edges of the slits, and seeing if the interference pattern shifts measurably, even when the photon energy and the total number of photons, flux, remain constant.
Physically changing interference by coding the slit edges. That would be revolutionary.
It absolutely would. These are the exciting, challenging next steps for this field. If these kinds of experiments succeed, it would represent a groundbreaking validation of the framework's power to describe and potentially manipulate physical reality. If they fail, well, then the specific physical hypotheses linking the math to these phenomena need reevaluation. Maybe the coupling isn't as simple as modeled. But the mathematical elegance and internal consistency of the core framework, the provable parts we listed, would still stand as a powerful theoretical achievement in its own right. Hashtag the something from nothing chain in exact steps.
Okay, to bring this all together, let's trace that elegant chain one more time. The one that explains how geometric form and localized energy can emerge from seemingly simple changes in this underlying phase field. You called it the something from nothing story earlier, but it's really something from structure. Let's lay it out in exact provable steps, tying everything we've discussed into a single, cohesive, logical narrative. This feels like where all the mathematical rigor we've explored truly culminates.
Absolutely. This chain of rigorous implications is really the core aha moment of the entire framework, I think. It demonstrates how these abstract mathematical principles cascade step by logical step into a complete and self-consistent explanation for the emergence of localized energy, clearly defined boundaries, and even spacetime curvature itself, all fundamentally driven by the configuration of the time phase field β. Let's walk through it, and remember, each step we take now is intended as a rigorous, derivable truth within the mathematical formalism we've outlined.
Okay, step by step, let's hear it.
Step 1. The journey begins with the simplest state, baseline. If our time phase field data is perfectly constant everywhere, meaning its gradient, partial theta, is 0 everywhere,
No change, no variation.
then its associated stress-energy tensor is identically 0. This rigorously implies that an undivided, perfectly smooth time, where the phase field is uniform and unchanging, carries no localized energy or momentum whatsoever. It's a state of pure, undifferentiated potential. A blank slate, geometrically speaking. Provable from the definition of 2's.
Okay, uniform phase is zero energy contribution.
Step 2. Now the first crucial change. When the phase field of theta folds, when it actually varies across space-time, so its gradient partial theta becomes non-zero in specific regions, then its stress-energy tensor is no longer 0 in those domains or along the walls where the change is happening. That difference from 0, the non-zero value of theta, is precisely the energy density and momentum flux that becomes localized in space-time.
The gradient itself is the energy source.
It represents the localized energy momentum. This is the crucial mechanism by which energy, or localized something, effectively comes into being, or rather, becomes manifest directly from the specific configuration or structure of the field. It's not created from nothing, but manifested from the field's organization. This follows directly from the mathematical formula for θ.
Okay, phase change generates stress energy.
Step 3. These localized regions where the phase field varies rapidly, where its gradient is significantly non-zero, often manifest as those stable boundaries or interfaces we discussed. As we established earlier, these boundaries are rigorously identified as the kink solutions, or domain walls, which are specific, stable solutions to the Euler-Lagrange equation derived from our Lagrangian.
The stable boundaries are solutions to the field's own equation.
Exactly. They are the natural lowest energy configurations for transitions in the phase field, like the most efficient and stable way to create a fold or a division between different phase regions. Their existence and properties are provable consequences of the variational problem.
Phase folds make stable walls. Got it.
Step 4. Now, given these precisely defined boundaries, kink walls, and the localized energy densities associated with them from step 2, the overall geometry or shape of a physical system emerges. This geometry is simply the spatial arrangement that minimizes the total energy for the entire coupled system. This includes the energy stored in the phase field's gradients and potentials, plus the energy of any other matter fields, etc., coupled to it.
The final shape is the minimum energy shape.
Yes. This is a fundamental and provable principle of physics derived from variational methods. Systems naturally tend towards stable minimum energy configurations. The specific geometry we observe, be it a crystal lattice, a leaf shape, or a pattern in a fluid, is a direct reflection of this energy minimization process, where the phase field theta plays a crucial role in defining that energy landscape.
Minimum energy determines geometry.
Step 5. Finally, closing the loop back to gravity. This localized energy density and momentum generated by the phase field's configuration, step 2, and organized into a specific geometry, step 4, directly influences spacetime curvature. Space curvature responds precisely via Einstein's field equations. The stress energy contributed by our phase field actively warps spacetime, creating the gravitational effects we observe.
The phase field's energy curves spacetime.
Precisely. And what's absolutely crucial to hammer home here is that each arrow, each step, each implication in this 5-step chain is a rigorous implication derived directly from the variational formalism in established physics, like general relativity. This isn't speculation or analogy. It's a derived mathematical sequence where every single step logically and provably follows from the preceding one. It builds coherently from abstract phase gradients to tangible energy density, to defined boundaries, to minimum energy geometries, and ultimately to the curvature of spacetime itself.
At the ultimate aha moment, seeing it all laid out.
Exactly. Seeing how abstract mathematical principles, starting just with phase, can cascade through rigorous steps into a complete, self-consistent, and potentially provable explanation for the emergence of energy, structure, form, and gravity in our universe. #outro.
What an incredible and, yes, rigorous journey we've just taken. We've plunged into the profound mathematical depths of this time-phase field framework, exploring how it can potentially explain form, curvature, and pattern selection across so many different scales. And we've meticulously seen how much of this framework is already proven within established physics and mathematics, from the dynamics of those stable kink walls to generating complex geometries like spherical Fibonacci patterns from irrational numbers, and even how it refines our understanding of EMC22 by adding that geometry factor.
That's right. The sheer rigor of the derivations, starting from foundational principles like the Lagrangian and variational calculus, and following the logical consequences through standard mathematical techniques, really underlines the solidity of the core mathematical structure here.
Indeed. And the core insight throughout this deep dive feels truly remarkable. That by merely changing time's fractions or subtly adjusting the phase of this fundamental field, the mathematics unequivocally shows this can lead to vastly different forms and energies.
Exactly. The derivations reveal this internal consistency that is, frankly, stunningly elegant. You see the chain, phase field dynamics rigorously create boundaries. These boundaries mathematically manifest as localized energy density. This energy density then, through standard GR, curves spacetime.
And the other chains too.
Right. We saw how symmetry-selective couplings in pattern formation equations rigorously switch the selection between hexagons and decagons, and how a mere phase shift in wave superposition, even at fixed total energy, provably results in entirely different geometries via the nodal patterns. These aren't just ideas. These are derivable, provable consequences of the underlying mathematical structure we laid out.
And this brings us, I think, to the most exciting part. The clear and precise demarcation between what's theoretically robust, mathematically proven, and what now requires empirical validation in the real world.
Precisely. The beauty of this framework, approached this way, is that it doesn't leave us just guessing. Instead, it points directly, almost like a treasure map, to a thrilling next chapter. a chapter that involves building those highly specialized experiments, the fixed energy phase-only rigs for morphogenesis or pattern switching, and those incredibly precise symmetry-matched Casimir cavities.
To physically test these profound predictions in the lab, it really is science at its most fundamental, isn't it? Moving from rigorous mathematical proof to the ultimate arbiter, experimental verification.
Absolutely. So we leave you, our listener, with this provocative thought. If these experimental predictions do hold true, if we actually can measure those tiny Casimir corrections tied purely to cavity symmetries, or if we can reliably switch biological patterns or material ordering just by tweaking phase fractions at fixed energy,
What would that mean?
it would mean we gain a quantitative geometric handle on shaping form, on shaping reality perhaps, by merely tuning time's fractions. What unexpected forms could we then create? What novel materials could we engineer with properties dictated by phase geometry? Or what fundamental mysteries about the universe's own blueprint could we finally unlock simply by learning to adjust and orchestrate these deep underlying rhythms of existence?
It really encourages all of us to reflect on how a simple concept like phase, something we often overlook in our everyday understanding of the world, might actually be an incredibly potent foundational principle for shaping literally everything around us, from the smallest subatomic interactions to the largest cosmic structures. Perhaps the intricate dance of phase is the hidden conductor of reality's grand symphony.
A beautiful way to put it.
Thank you for diving deep with us today.